I'm going to be covering some ground I've already covered, which is not going to hurt. The chemical reaction is it has a particular structure, and we need to talk about the structure because your use of the chemical reaction will depend on your understanding of the structure. So we're going to talk about it. And in that context, we'll talk about its elements. Now, the elements of a chemical reaction can be shown in, let's just take a chemical reaction, for example. Let's take a reaction such as iron reacting with oxygen to form Fe2O3. That's an incomplete chemical reaction. The expression of chemical reaction, it's incomplete. And there's some reasons why it's incomplete. And we're going to go over that. And we've talked about it, as I say before. And one of the things that to call your attention to is the balancing. It's critical for what's coming up for us Friday. When I want to talk to you on Friday, you have to understand how critical balancing a chemical equation really is. And so in that context, I want to balance this. First of all, let's talk about molecular formulas. That's a molecular formula. So is that, as a matter of fact. That's a molecular formula. This is just simply an atomic symbol. It tells us the presence of a particular atom, in this case iron. Well, how do we come up with molecular formulas? Well, first of all, if we didn't start here, if we didn't know this, all we could say is that we had some Fe and some O. And those X and Y are subscripts, and we have to be able to determine what those are. Now, I should point out, to relieve a little of your attention, is that normally you don't have to do this. Normally you don't have to do this. But I need to go through it because I need to impress upon you the necessity that once you have a formula, don't change it. If you're if you have it on authority that it's a correct formula, don't change it. If you change it, you'll change it to another chemical, and then the reaction no longer has meaning within the context that you've already established. So we have to determine this. Now, each of these elements in compounds have oxidation numbers, or charges if you want, that they exhibit. For example, iron can either be +1, +2, or +3. Well, we don't know which one that is. Now, how do you know these numbers? Well, I gave you a piece of paper. It was printed on both sides, and it had elements and it had the many of the elements, and it had ions and nonmetals and so forth, and polyatomics, and it told you the preferred oxidation numbers. That's what this thing is called. And one of the things you would see if you look is that oxygen is always, for our purposes, is always -2. Okay, so here's the thing. If you don't know what this is here, that is the correct molecular formula here, you have to figure it out for both of them. So in the first case, let's say iron is +2. And you have to solve for X and Y. Well, intuitively, you can look at the objective is this. We want that whole thing to be neutral. It shouldn't have a net positive charge, it shouldn't have a net negative charge, it should be neutral. Let me put it another way. It should have as many negative charges as positive charges, because if that were the case, it would be neutral. Well, each iron is carrying a +2 charge, and each oxygen is carrying a -2 charge, so the lowest possible numbers that we could have, the smallest possible numbers we could have for subscripts would be 1 and 1, right? Because if we put a 1 in here, and a 1 in here, then we have 2 pluses and 2 minuses, so we've met that requirement. We've met that requirement with this formula. Now in chemistry, we don't usually put the 1s there, 2 and above. We put 2 and above there as necessary, and we also don't put this in here because as a chemist, we look at this and we say, well, that's implied. We know that has to be the case. In other words, the charge on this has to be the same as the charge on that. We know that by looking, just by looking. Well, that's in a case where iron is in a +2 state. How about when iron is in a +3 state? Now we have to solve for x and y. There's a very simple way to do it, and I recommend, you probably are way ahead of me, you know what it is. You simply use the subscripts, the oxidation number of the other atom. In other words, x would take on that number there, 2, and y would take on that number there, which is 3. Now that's just a recipe. It's just a recipe. It doesn't tell you why it works that way, but we could prove it by generating some algebraic equations here and solving for x and y. We know the sum. We know what the sum has to be, and that's one equation, and the other equation is weighted by, you guessed it, 3 and 2, with sum. So with those two equations, we can solve for x and y. You know that because you took algebra, and you know what you're able to do with 2 equations and 2 unknowns. You can solve for both of them. But the easiest way for us to do, given the time constraints that we have during exams and that sort of thing, is to simply take that number there, 2, and use it as the subscript for the metal. And take the oxidation number for the metal and use it as the subscript for the nonmetal. That's why the 3 is there. The easiest way. Because look what happens. If you do that, 2 times +3 is +6. 3 times -2 is -6. If we sum them algebraically, we get 0. Okay? That's why you're allowed to do that. Okay? Now, if you're given no other information, I'm going to get rid of some of this, all this nuts and bolts stuff here. We don't need it. Without additional information, we don't know what it is. We don't know what it is. We're free to assume it's one or the other, but without additional information, we simply do not know what which oxide of iron is being designated here, because we don't have any other information from this side over here. Let's suppose that we try. We would have to do it for both, and that's easy enough to do. For example, if we have iron plus O2, it's going to give us this first oxide, FeO. Well, it looks like it's balanced for iron. Remember, the basis for balancing is the law of conservation of matter, or mass. which simply states you can't create or destroy mass in a chemical reaction. You can't do it. And that, if that's true, then we're safe in saying, well, this is a chemical reaction, so the mass on this side has to equal the mass on that side. Another way to say it, and you may find this more accommodating to your needs, they have to have the same number of atoms of each kind on both sides. So far you have one here, you have one here, so it looks pretty good. Here you have 2 atoms of oxygen, because this is just, that's oxygen, with this double bond there. And it has a bunch of electrons making up a stable octet. In any event, we have 2 of them, but we only have 1 over here. It's not balanced. And so how are we going to balance it? We never, we're not going to change subscripts now. Never change them. So we come over here and we put a 2. Now it's balanced for oxygen. But in putting that 2 there, we also multiply the iron, because coefficients multiply both sides of the equation. Excuse me, they multiply both elements in the equation, or all of them. It could be more than 2. Okay, so we have to go back and say, okay, we now have 2 irons here, and we only have 1 over here. So if I put 2 there, it's now balanced, because I have 2 irons on one side, 2 irons on the other side of the arrow, and I have 2 oxygens on one side and 2 on the other. So it would be balanced. Now, let us suppose that we said, yeah, but what if it's this oxide of iron? Will it also balance? Has to. It has to. So let's try to balance it for that. I have 1 iron on this side, and on this side I have 2. So I'm simply going to put a 2 there. All right? Now it's balanced for iron. I have 2 oxygens on this side. Whoops, I have 3 on that side. Now, there are a couple of ways to attack this particular problem. You may say, well, what if I had one and a half O2s? What if I had 1.5? I'd have 3 oxygen, right? So if I had 3 oxygen, then it would be balanced. It would be balanced. But chemists get really nervous and uptight when you use fraction, particularly this type of fractions, ratios. They really don't like that kind of fraction because they don't understand it any better than you do. So what are we going to do? Well, you can turn this into an even number by multiplying through by 2. Not an even number, excuse me, a whole number. By multiplying through by 2. Multiply through by 2, and you get 3 here. Multiply by 2, you get 4 here. Multiply by 2, and you get 2 of the molecule product. The thing to remember is if you're going to multiply anything by change a coefficient, it has to come out even. For example, multiplying by 2 made this 4. So I had to go through it by 2. If you don't believe it, there's 4 irons here now, and they're 2 times 2, or 4 irons in that in this molecule. That's what we want, 4 on each side. We have 3 times 2, or 6 atoms of oxygen, and we have 2 times 3 atoms of oxygen, or 6 on this side. So it's balanced for oxygen, it's balanced for iron, it's balanced for its mass. Because you have the same number of the sources of mass on both sides of the arrow. So it has to balance if you do it that way. So that's another way you can do it. Another way you can always do it, and I'm not necessarily recommending this, but it always works. If you, let's see, let me do this. You notice you have 2 of these on this side and 3 of these on this side, right? What if you multiplied both this by 2 and this by 3? You would now have 6 on this side and 6 on that side. So now you'd be balanced for iron. And you've got to fix iron over here because you've got 4 of them over here. And so you could do that. Notice that every one of these is neutral. The ones you're particularly worried about are these over here. Well, that springs from having the correct molecular formula. And of course, this has its oxidation number is 0, so you're all right already on those. Okay, this is the essence of writing a correct chemical equation, and these are the elements of it. The first thing you have to do is you have to find your molecular formulas, and you do that by paying attention to subscripts. While you're determining the molecular formula, you're not fooling around with coefficients at all. You're not doing anything to coefficients. That comes when you introduce a molecule into an equation. That's when you use coefficients. Okay? Once you have the correct molecular formulas, you now can write chemical equations. And the first thing you have to do, once you write them, you have to balance it. It has to obey the law of conservation of mass, or matter. And you do that with coefficients, not with subscripts. Never with subscripts. Balance it with coefficients. Okay? Now, let's shift gears a little bit and use some of the things we've learned here to talk about types of reactions. Your author does not include as a category of a chemical reaction known as a combustion reaction. A combustion reaction is a type of reaction that is being carried out in every cell in our bodies, every moment of our life, every moment of our life. Somebody told me, I think I believed him, but I don't remember who it was, so maybe I didn't believe him. Anyway, somebody told me that a human being has 3 trillion cells in their bodies that carry out metabolism. And what really is metabolism? Metabolism is an oxidation reaction. That's what it is, and we use in our bodies we burn glucose and oxygen, and the products are and here's what your body is really after. Because for all intents and purposes, it throws away all the rest of that stuff. It gets rid of it. This was the point in eating your Wheaties this morning with sucrose or sugar on it. That's why you did that. From your cell's point of view, from each cell in your body that carries out metabolism. So metabolism is really another word for oxidation. Oxidation reaction, and we also know it by metabolism. And we haven't balanced this equation, and maybe we better, otherwise we'll lose credibility. We have 6 carbons on this side, so I'm going to use a coefficient on this side to balance it, and what number will that be in front of the CO2? 3, 6, but who said that? Because I'll tell you what's wrong. You're thinking that subscript applies to the carbon as well. The subscript applies only to the element to the immediate left of it in the formula. The next one over, as you're looking at it, doesn't apply. So now let me ask you the question. What is the coefficient going to be?
6.
6, that's right. All right. So if we say, well, for carbon it's balanced. Okay, let's look at hydrogen next. We have 12 on the left, and we have on the right, hydrogen is occurring 2 at a time. So how many, what's the coefficient going to be for this?
6.
Correct. And now all we have left is oxygen. So we have 6 oxygen here, and we have 2 here, a total of 8 oxygens. And let's see, am I right? Yeah, 8. 8 oxygens over here. This is oxygen atoms. 1, 2, and 6 is 8. That's where that 8 comes from. Over on this side we have, for every one of the CO2s, we have 2 oxygen atoms. But we have 6 of them, so that's 12. And over here we have 6 oxygens, that's 6 more. So we have 18. Okay? Now these oxygens are occurring 2 at a time. Let's see. 2 at a time. Now, we have 2 places to account for oxygen, and the most convenient thing to do is take these away from the total. Now it's 12, and we have to take the 6 away from here. That's 2. So 2 times something has to equal 2 times x has to equal 12. And the algebra for that says this has then to be 6. All right? Let's see if that's right. 6 times 2 is 12, plus 6 is 18. Over on this side we have 12, plus 6 is 18. So it's balanced. So the chemical equation is balanced, in this case for glucose. Now, this is an oxidation reaction, and it also falls in the same category as a combustion reaction. It's called a combustion reaction. Okay? There's only one reaction in your body. Actually, there's a couple more, but limited number of reaction types in your body that burns, if you will, or combusts glucose. There are millions of reactions where combustion occurs. Come on in. Put the money around the corner and take a seat up front. There are millions of combustion reactions, but they include, this is a main one that they include from biochemistry point of view, because it's happening every place. Now, how much heat is being generated? If we're in here in this room for, let's see, 1 hour. each of us during the 50 minutes that we're here will be consuming sufficient energy to light up a 1-watt light bulb. Well, that's no big deal. That's less than a refrigerator light. But let's say if we had everybody here who's supposed to be here, we would have a 50-watt light bulb. 50-watt light bulbs are, I'm talking incandescent light bulb. That's a substantial amount of heat. Just in the 50 minutes we're here. So this is not an insignificant amount of heat. And then when you start using multipliers like 305 million people in the United States, how many 100-watt light bulbs could they light up? I might put that on your next exam. No, never mind. We could figure it out. We could figure out, you know, it might light up one searchlight that would illuminate the moon. Who knows? I mean, we'd have to make the calculation to figure it out. But this is the reaction that's going on. And glucose is the primary reactant that takes place. That's this one right here. And oxygen. So this is an oxidation as well. We refer to it as an oxidation. Okay. Now, there are other kinds of reaction. And your author doesn't list, as a matter of fact, doesn't list combustion as a reaction. She calls it a decomposition reaction. That isn't entirely clear to me, but she has a decomposition and one example is Mercury Oxide. If you heat it up, you get mercury, the metal, actually it's a liquid, plus mercury, the metal, and this is a solid. And if you just heat it up, all you have to do is heat it up, and it'll turn to a gas, oxygen, and a metal, a shiny liquid metal will appear. This is a decomposition reaction. Many decomposition reactions, for example, potassium chlorate. Potassium chlorate, if you heat it, will make this little. Okay, now we can apply our rule. We want to balance for oxygen on both sides, so we're going to multiply the whole molecule times that subscript, and the oxygen, we're going to multiply it by this subscript here. So now I have 6 oxygen there and 6 here. I'm balanced, and I have 2 KCl's, and I'm balanced. So it's simple, if you notice that. If you don't, it's a nightmare. Anyway, this too is decomposition. All you have to do is take potassium chlorate, and potassium chlorate is what you would get if you took household bleach and cooked it down to, carefully, cooked it down to make a solid, which would be sodium chlorate. Sodium chlorate. It turns out sodium chlorate is also a right handy explosive, can be explosive, act as an explosive. It's even more, the chlorates are even more explosive if there's a proton right there, and it makes another chlorate that will blow up smartly. All right, well, this is decomposition type of reaction, and that's one that your author lists, and therefore you should feel as though you're responsible for being aware of that reaction. She uses symbolism, and this is why she does decomposition. She says, suppose you have a, let's be, and you heated it up. Excuse me. You have AB, get B, C. I'll get it in a minute. Let's see. There was one thing, you heat it up and it turns into two things that are different from the first thing. And that's what we were talking about when we talk about decomposition type of reaction. Okay, well, are there any other kinds of reactions? Yeah, there's one called a single replacement reaction. I'm going to get rid of this just to get a little space here. A single replacement reaction.
Hey. Thank you.
Zinc chloride, and let's say you dissolve it in water, so we'll make this AQ. We'll put AQ to indicate water, and wait a minute. Zinc, we start out with zinc, and it's a solid, and we're going to add HCl, and this is of course normally a gas unless I put AQ there. If I put AQ there, it's not a gas anymore. It's dissolved in water. HCl is very, very soluble in water. And we know it also by hydrochloric acid. And those of you who worked in the construction trades, particularly masonry, you know that you clean masonry by using muriatic acid. That's another name for hydrochloric acid. But if you add these together, you get and this is a solid plus H2 is a gas. It's a gas. And this is a single replacement, meaning that this will take the place of this. But the thing that of the hydrogen and make zinc chloride ultimately. The thing to notice, however, is that the oxidation state of zinc is 0 there, and the oxidation state of hydrogen is positive there, and the oxidation state of zinc here is +2. The oxidation state for chlorine is that, and the oxidation state of hydrogen is 0. So, what's happening? Oxidation is happening. Okay, how about right here? Reduction, oxidation reduction reaction. It's also, in this case, a more specific form of an oxidation reduction reaction is a single replacement reaction. Okay, the single replacement reaction just shows these two swapping places, hydrogen and zinc. Okay, a single replacement. Now, there's another one that's called double replacement. And double replacement could be something like oh gosh, let's see. Zinc sulfate plus nitrate plus NaCl. We'll go to silver chloride. And that's a solid. These are all AQ, AQs, AQs. That's a solid plus sodium nitrate. It's double replacement, and this is AQ. AQ just means it's dissolved in water. That's all it means. All right. Notice double replacement. What happened was that silver took the place of the sodium, and the sodium took the place of the silver, and that's all that happened. If you do that, you come up. If this takes the place of silver, you have sodium nitrate. If you do, and the silver then takes the sodium's place, and you have silver chloride. Now, this is a reaction that occurs spontaneously. If you do it in lab, and you will, one of our labs will have that reaction. You will have a, it's kind of spectacular how the reaction occurs. It happens immediately, for one thing, and in tremendous volumes of solid. Now, this is not an oxidation reduction reaction. It is not an oxidation reaction. This one is. Many or most of these are. So these are two, let's see, we did decomposition, we did single replacement and double replacement, and let's see, what does your author, I can't remember what her convention is. The problem is there are about as many lists of types of chemical reactions as there are people who write books about them. Your author has one other type of reaction that we can talk about, and that is, let's see, I'm going to erase this, what she calls a combination reaction. A combination reaction would be, for example, Md metal, so that's a solid, O2, a gas, MgO, and this is combination. I read myself. Okay, this is a combination reaction. Very common. Carbon does exactly the same thing. And carbon dioxide. One of the products is often a gas. Oxygen will frequently form will be one of the reactants. But notice another thing too. It's also an oxidation reduction reaction. Oxidation reduction, because and the reduction part is the reduction. What's referred to as reduction? Well, there's a message, and it's the message that I'll leave you with as far as our talk here today, is that whenever you have an oxidation reaction, you absolutely have to have a reduction reaction. You have to. And here's why. We'll take a look at that one right there. That reaction, magnesium and oxygen. Let's just write the oxidation reaction. So we have Mg, the element, and, pardon me, it's going to produce Mg, the ion, plus 2 electrons. All right, let's look at the oxygen. Well, let's just look at atomic oxygen, just for the time being. Actually, we can do O2, it doesn't matter. Okay. This is a reaction where the oxygen takes on 4 electrons. Remember that oxygen is looks like that, and when it takes on 4 electrons, it has 2, 6, let's see, 4 and 4, 8, stable octet, takes on 4 electrons. We have 2 of these oxygen, but when we have that, it's -2. Okay, the charge is -2 on each one of them. Well, this is an oxidation reaction, and this is a reduction reaction. And this has to get electrons from somewhere to happen. Remember, I said they happen together. So the metal serves as the source of electrons for the nonmetal to produce to carry out the reduction. In other words, one of the products of the oxidation reaction is a reactant in the reduction reaction. Okay, that's why I said they have to occur together. You can't have just one. I had an oxidation reaction the other day, and boy, was it great. I don't believe you for a minute. You must have had a reduction reaction too. Tell me about that. Now I'm impressed. All right. Well, that's the thing you have to realize about oxidation reduction reaction. There's a little acronym that your author would like you to remember, or offers you, that in the case of Leo. Wait, that's not Leo. That's Loey. Leo. And down here we have loses electrons, oxidation. This is oxidation because it loses electrons. They appear on the product side. Gains electrons, reduction, the electrons appear on the reactant side. Okay. A lot of people remember this and solve, come up with answers to questions in exams. and have no idea what they're talking about. But if they remember that, they get the point. And I'm sure you get the point. So if you have any choice at all, have a nice day.